Up until now, what we've done is given the motor some values and they would move to these angular positions. But it is a lot more comfortable and realistic to give the robot a position in XYZ coordinates that we want the robot to read, and the robot will, well, actually the microcontroller will have to calculate the values for each one of the joints. Because of this, we should implement the inverse kinematics of this robot. So in this video, we will see how they were programmed, and we will implement the function moveJ, with which the robot will move from a point to another point, calculating itself the values of the joints, but the trajectory is random. It means it's not linear, it's not circular, it is just the most comfortable one for the robot. This is the code for implementing the inverse kinematics of the robot. So first we have what we always have, there's nothing new here. And now there are these two data types that are new. This first one is a vector which contains all the parameters of the robot, that means the measurements of the beams, for example, or the height. And this one is a data type, a vector that will include the x, y, and z position. So, well, this is the same, but now we are putting the values of the parameters. These values can be consulted in the slides, and you will see that these are the values of the robot. And well, here, using this new data type, which is robot position, I have put some values. This first one has been calculated so that it coincides with the position that the tool has when all joints are at 90 degrees, which is considered like the home position. And here I have declared some vectors that will contain the value of the joints at each one of the positions of these positions. The first one, of course, it is the home position. The values are 90, 90, 90. This is the declaration of the created functions, and here we have the code. But first, let's go to the function implementation. Well, we have already explained right servo and detach servo. We have explained to moveJ, which is the one responsible for the smoother trajectory, a polynomial trajectory. And now we have moveJ and inverseKin. So inverse kinematics receives the target point, the parameters of the robot, and it stores in a variable q the value of the joints for the desired position. These are the equations needed to calculate the inverse kinematics of the robot, and they can be consulted in the slides of the course. But there's this difference. If you recall, there's a difference between how joint 3 moves in the simulation and in the physical robot, because in the physical robot, they have different sense of rotation in this motor. So the way to solve this is, for the simulation, it will follow this equation, which is this one, but pi minus this. What this does is changes the sense of rotation. And well, finally here, as the program calculates in radians, but the robot takes a position in degrees, the motor, sorry, here we are just changing the values to degrees. The function moveJ calculates inverse kinematics for the, the function moveJ receives the servos whose position has to be changed, the initial values of the joints in the initial point, the target position in XYZ, the time for the trajectory, the parameters of the robot, and the direction of another vector in which it will keep the values of the joints in the target position. This is really useful because then when we go to the code, we will see that this will be needed for the next instruction in this parameter. We will see it later. So what we have here is that it calculates the inverse kinematics of the target point and puts the value of the joints in Qt, and then with moveJ we calculate the polynomial trajectory from the initial angles to the final angles during this time. So let's go to the code, which is here. Well, first the initialization of the serial monitor, which we will see now, and here, okay, we are going to the initial position, and then we are moving from Q0, that is the home position, to the first point in 2 seconds, and in Q1 the value of the joints in the target position is stored. These lines here write the value of Q1 in the serial monitor, and well, we are doing this again and again from the initial position to point 1, from point 1 to point 2 we have Q2, from point 2 to point 3, from point 3 to the home position, and detaching the servos. Okay, so this is the series monitor, and now we will start the code. So well, you can see that the positions are changing, and in the final position we see that these are the values of the joints. We go to the next point, these are the values of the joints in the next point. And now we should go to the third point, and this is the value of the joints in the third point. Finally, we go to the initial position, so the values should be 90, 90, 91.8, which is really close to 90. Now we're seeing the code in the simulation, so we will run it. And now you'll see that it is going to the points that we desire. I am not able to remind the points now because of a problem of the recorder, but with the physical robot I will put a reminder of what the points were, so that we can see that the robot is effectively arriving at these points. Okay, so these are the points, and I have written them in a notebook so that they are easier to see. So the first point, well, these are the axes, and well, the axis set is going upwards, but I couldn't draw it. So the first point is in 100, 70, and 150. So it should be 100, like around there, then 70, and more or less I have thought that it should be here in point 1. Now the second one is 20 minus 180. So if that's 20, then it should start there and go until there, where there's the second point. And finally we have the third point, which is 170 and 100. So 170, it must be more or less in here, and 100 from there should more or less be here in the third point. Now about the heights. 150 is a little bit higher than the initial height of the robot, 100 is a bit lower, and 30 is really low. So let's see if the robot reaches these positions. Okay. Now it must come here with a position a little bit higher than before. Now to the second position with a bit lower. And finally to the third position with a really low height. Okay, so as you can see, the positions have been reached as we wanted them, so we can consider that the inverse kinematics are achieved. So in this video, the inverse kinematics have been programmed and the robot can move to the target positions with this code. However, the path that it will follow doesn't have any specific shape, it's not linear, it is not circular or whatever. So in the following task, what should be accomplished is to move to other positions following a specific path.